Good morning. I did not grade your quizzes yet, but I will do that, and then I'll get you back those grades tomorrow, and I will spend some time during class tomorrow discussing them. Okay? All right. But today we're going to talk about something called measures of relative standing, and then maybe if we have time, density curves. Okay? So measures of relative standing. Okay? And I don't want to give this away. I think I'm going to start with a question and see what you think. And then afterwards, you'll tell me what you think. All right? So this example is on page 118 of your textbook. It's example 2.2. And here's what it says. So I'll read it to you. The day after receiving her statistics test result, excuse me, of 86, okay, from Mr. Pryor, Jenny earned an 82 on Mr. Goldstein's chemistry test. At first, she was disappointed. Then Mr. Goldstone told the class that the distribution of scores was fairly symmetric with a mean of 76 and a standard deviation of 4. So let's make a note of that. That was on the chemistry test. Okay? So we have this person, Jenny, and she took a chemistry test. And on the chem test, she scored an 82. And what we know about the chemistry test is that the mean of the chemistry test was a 76, and the standard deviation of that test was 4. Okay. On statistics, she scored an 86. Okay. However, the statistics test was a little different. The mean there was a 78 with a standard deviation of 6. So the question I want to ask you is, which test did she do better on? That's what I want to know. Well, what do you want to say? What do you want to say right away? Statistics. You got an 86, right?
But based on that information.
Yeah, sure. What are you worried about? Let's talk about what this information measures, right? Tell me about X bar. What property of a distribution does that help us find? The mean. It's the mean, right? And it measures. It's one way of measuring the center. Now, we did mention the words fairly symmetric. He said the distribution of grades is fairly symmetric. Does that mean it would be okay to use the mean to describe the center or not?
Yeah.
Jessica's saying yes, it would. Ben, you agree? Can you tell us why? Okay, great. Okay. So it's okay to use mean to describe the center of the distribution. What about this S? What's that stand for? I think I said it before, but just in case we forgot. Standard deviation, right? And what aspect of a distribution does standard deviation measure? Want it? Spread of the distribution. Okay. Now I asked this a few weeks ago, or a few days ago, that is standard deviation resistant or non-resistant to the effects of outliers? Let me ask the question another way. If we take the highest number in a data set, we make it much bigger, will the standard deviation be affected? Kevin? That's correct. It will. And if you think about the standard deviation formula for a minute, you know why. So standard deviation formula, S equals the square root of 1 over n minus 1 sigma xi, which is one of our observations, minus x bar, which is the mean, squared. Okay? Is it fair to say that standard deviation depends on the mean? Jessica, what do you think? Yeah, how come? Sure. The mean is inside the standard deviation formula. So if we change this number, isn't this whole calculation going to give us a different number? So if mean is non-resistant to the effects of outliers, then what do you know about standard deviation? It's non-resistant to the effects of outliers. Because you can get to know that. That's why people ask me, hey, do I really need to know this formula? Not really. But if you know about it, you see the question you could just answer? Right? It was much clearer now. Okay. So I'll go back to our original set of data here. Is it okay to use standard deviation to measure spread in this situation? Ben, what do you think? Ben says yes. Raise your hand if you agree with him. What words did we say earlier that leads you to believe that this is okay? Jonah? Right. And in a symmetric distribution, we have the mean in the middle, right? There could be outliers, but we're going to say symmetric with no outliers for the time being. Okay. Thanks, Jonah. All right, so I go back to this question again, which Emily said earlier, I think this is a trick question, right? I mean, you went home and talked to your parents, you'd say, oh, 86 to 82? Well, you did better on stat. What happened in chem, right? Probably what they'd ask. Let me exaggerate for a minute. Let's pretend the mean on the stat test, right, had been 92. Let's pretend that for a second. Now what test did you do better on? Emily's changed her answer. Jessica, you agree? Jessica agrees. Who agrees that in this situation now, this person did better on her chem test? Yeah, right? Simple reason. Why would you say that?
Because the mean changed, so like most of the people test got 92.
Right.
So
She fell under the mean. The average kid got a 92, and she got less than that. Okay, let's go back to what I originally said that number was. I think I said 78. Is that right? Okay, what makes this question a little harder to answer? Kim, what do you think? All right, so both test scores are slightly above the mean. Here's what I'd like to know from you. I'm going to ask you a question and then tell you what this is about afterwards. How many standard deviations above the mean did she score on the chemistry test? Right? And then I want you to compare that to how many standard deviations above the mean she scored on the statistics test. What do you think? All right, Aaron, let's hear from you. She scored more standard deviations above in the chem test. How many? Do we know how many standard deviations she scored? 4 standard deviations above? 1.5 standard deviations above? Do you guys agree with that? Where's he getting this number? What does he mean 1.5 standard deviations above the mean? Kitten, what do you think? The formula x minus the mean over standard deviation. I'm willing to bet a lot of you haven't heard of that formula. Let's talk about it. X minus the mean over the standard deviation. Okay? We could also think of this like the following. It's the observed score minus the mean over the standard deviation, just like that. X means an observed score. And in this case, if we think about it, the chemistry test grade was an 82. The mean was a 76. And this formula is telling us to divide by 4. But let's talk about why that's the case. When we do 82 minus 76, we're finding how far apart those scores are, right? Would you agree we get 6 for an answer? Okay. And then we're dividing it by 4. We're saying how many 4s are in 6, right? So there are 1.5 of them when you divide. So the meaning of this 1.5 is the following. Jenny's score of 82 is 1.5 standard deviations above the mean. Now, how can I use this idea to see if she did better or worse on the stat test? What do you think we could do now? Jess? Right, you find the same thing for the stat test, and that's what you'd have to say, same thing, because I haven't given this thing a name. Just so you know, when you do this, when you do z equals x bar, I'm sorry, not x bar, my bad. You do x minus the mean over the standard deviation. Now I'm just giving you some new notation. If you see this thing here, it looks like a U with lines on the side of it. That's called mu. It's x minus mu, but mu stands for the mean, and that's the standard deviation symbol. This thing is called a z-score. Or sometimes it's called standardized score. And it turns out this is a very good way to make comparisons like this. Okay? So let's look at the information for the stat test. She got an 86, the mean was a 78, and the standard deviation was 6. So who wants to fill in the z-score for us? What would happen? Z equals. Go ahead, Lara. Over 6, right? Standard deviation is a little bigger this time. And what do we end up with? Ben, you got this? 1 1/3, so 1.333. All right. So who can write a sentence or tell us what the meaning is of this 1.33? Say a sentence like the sentence I wrote on the board earlier. What do you think? M?
Jenny's score of 86 is 1.33 standard deviation.
Perfect. I love it. That's exactly how you want to say it. Okay? So now I re-ask the question. Which test did she do better on? The chemistry test. That's right. Okay? So what z-scores do is give us a way to make comparisons when we're in two different distributions. And here's what I mean. If we had all the kids in Jenny's class, in her chem class, and we had all of their scores in a list, right, compared to the other kids in her class, right, she was 1.5 standard deviations above the mean. And similarly, if we had a second list for all the statistics scores, we'd find out that she was exactly 1.33 standard deviations above the mean. So what we can say is that she did slightly better relative to the class in chemistry than she did in statistics. Any questions? Yes, no, maybe. We're all right, right? Okay. So I guess what I'd like you to do is look at another problem. So you guys have textbooks.